Hey guys, today we're going to do section 3, which is on continuous growth or decay. So consider you invest $1 at 5% interest rate for 1 year. Complete the table below for the different compounding periods. So remember that our compound interest formula is P times the quantity 1 plus R over N to the NT, where P is your principal, R is your interest rate, N is the number of times you compound per year, and T is the number of years. So if I want to complete this, I'm just going to plug in the values that I know. So I'm investing $1, so my P is 1. Okay, my R value is 5%, so it'll be 0.05. My N value is the number of times per year that I compound. So if I'm compounding annually, that's 1. Okay, and my T value is the number of years. I've got 1 year. So when I compute that as a decimal, I get 1.05. Okay, now I'm going to do the same thing for semi-annually. The only difference is that semi-annually means that I'm compounding twice per year, so my N value will be 2. So when I compute that out, I get 1.050625. Okay, now I'm going to do the same thing for all the other ones. Quarterly means that I'm compounding 4 times per year. So when I compute that out, I get 1.050945. Okay, daily, it's going to be 365. And that gives me 1.051267. Okay, hourly. Well, I know that there are 24 hours in a day, and there's 365 days in a year, so if I multiply those two numbers together, I get 8,760. So if I compute that out, get 1.051271. And then per second, well, I know hourly was 8,760. I know there's 3,600 seconds in an hour, so if I multiply those two together, I get 31536,000. So that's my new N value. And when I compute that out, I get 1.052714. Okay, so this leads us to our compound interest formula when we compound continuously, which is PE to the RT, or what I like to call the PERT formula. Basically, what you'll notice is that if you use this compound interest formula, 1 times e to the 1 times 0.05, so I'm plugging in the values from my original equation, I get 1.05127, which is essentially what this number is approaching. The bigger and bigger and bigger my N values get. So if I compound continuously, I can just skip finding out what I need to actually approach, and I can just use this formula instead. So this is my compound interest formula. A equals PE to the RT, where A is the amount that I earn, P is my principal, R is my interest rate, and T is the number of years. And you'll notice that this is an exponential function. Okay, if you hit second and LN on your calculator, you'll see that E button. E is actually just a number, kind of like pi, how pi is 3.14. Well, E is just a number, I think it's like 2.18 or something. Let me check. So E is 2.718, and then it keeps going. It's an icky number just like pi is. That's why we have a letter to represent it. Okay, so you'll notice that E is actually the value that this function, our compound interest formula, converges to when n is approaching infinity. So as n gets infinitely larger, we're approaching this value e. Okay, so we're going to graph these on the axis below and state whether they represent exponential growth or decay. So if I graph y equals e to the x, you'll notice that that looks like this. Okay. So does that represent a growth or decay? That would represent an exponential growth. If I want to plot y equals e to the negative x, that one looks like this guy, which is a decay. All right, and that's everything for the notes for section 3.